Welcome back to the next video and to a new chapter, everybody. We now are going to be going after the proof of r equals t in the minimal case, which is all there is left to do to finally and fully proof r equals t. So this video, we're going to look at an important tool along those lines, and that tool is local Tate duality from chapter 4. So we will recall local Tate duality, and then we will prove a key proposition that we will need to prove r equals t in the minimal case using local Tate duality. So let's get after it. The setup, as in the general case, is that we'll fix a continuous representation, rho bar, from the Galois group of Q to GL2 of K, where K is some finite field of characteristic L and odd prime. We will assume that rho bar is irreducible, that its restriction to the Galois group at L is flat or ordinary, that it has cyclotomic determinant, and that it has square-free conductor. And the goal is to prove r equals t, and we've already proven r equals t in the general case for generic subscript sigma, assuming the minimal case. See video 11.2 and in general the previous chapter for all of the setup and work we did there. And so it suffices now to prove the following. Theorem, r equals t minimal case, the surjective ring homomorphism phi empty set from r empty set to t empty set, where the former is the universal type empty set deformation ring, and the latter is the, well, there's one of two ways of thinking about it, I guess. It's either the universal type empty set Hecke algebra, or I guess you could say it's the universal type empty set modular deformation ring. This is actually an isomorphism of complete intersection rings. Okay, so let's recall local Tate duality from chapter 4. Let's let M be a continuous discrete GQ module of finite cardinality. Let's let M star be kind of like its dual, so homomorphisms from M to mu sub n of Q bar. Mu sub n denotes nth roots of unity. And n here is just some integer that kills m. Observe that m star is still a GQ module under the usual dual action from basic representation theory. So throughout, this kind of wedge symbol or this V symbol here will be used to denote Pontryagin duality. So theorem, here's local Tate duality again for the second time in this playlist. Let V be a place of Q, so either finite or infinite. Then, first of all, the cohomology groups HI, GV, M, those are all finite for all I. And then, for all integers n, there are maps from h2 gv mu n q bar injecting into q mod z, compatible with the natural injections we have from mu n q bar to mu m q bar when n divides m. 3, if v is not the infinite place and I is 0, 1, or 2, then the cut product, see chapter 4, and the above embeddings from part 2 induce a perfect pairing from hi gv m cross hi to the 2 minus I gv m star to h2 gv mu n q bar, and then you can combine that with that injection to q mod z from part 2. So we have a perfect pairing here, okay, which is, I guess, like the central result of this theorem. Okay, 4, if v is not the infinite place, then hi gv m is actually trivial for I bigger than 2. What about the other i's? Well, there's a strong relationship between the cardinalities of those cohomology groups. The cardinality of h1 gvm is the same as the cardinality of h0 gvm times the cardinality of h2 gvm times the cardinality of m tensored up to z sub v. And then finally, if v isn't the infinite place and this guy m tensor zv is trivial, then the unramified classes h1 gv mod iv m to the iv and h1 gv mod iv m star to the iv are the exact annihilators of each other under the pairing from above from h1 gv m cross h1 gv m star to q mod z from, what number was that? Number 3. Okay, so I will not prove this. Milne's write-up in Arithmetic Duality Theorems, Chapter 1 is quite nice. What I will do is give you the proposition that we need that follows from this, and I will prove that. Okay, so let's go on to that. That's called Proposition 1, and it says the following. Let curly L be a collection of local conditions for M. Please go back to either the previous chapter or Chapter 4 to recall what that means. Then, the cohomology group H1 curly L QM is actually finite. And moreover, we have a very potent formula that relates a bunch of different sizes to a bunch of different cohomology groups together. Here's what it says. The cardinality of H1 curly L QM divided by the cardinality of H1 curly L star QM star, see chapter 4 or previous chapter for the definition of L star, is equal to the cardinality of H0 QM divided by the cardinality of H0 QM star times this cool product. It's the product over places V of the cardinality of L sub V, which is the local condition at V associated to this family here, divided by the cardinality of H0 GVM. And I'll just state for the record that Most of these LVs are on ramified classes. On ramified classes, though, as we saw in Chapter 4, their cardinality, that's the same as the cardinality of this guy down here. And so for almost all places V's, we get a cancellation here. And so we get a 1. And so this product is well defined. Okay, let's prove this. We're going to do a proof sketch. I will tell you that you can find all the missing details in one of two places. You can either go to the very end of CSS Chapter 4, or you can go to DDT, page 61, and you can find details on any missing information that I don't give you here. I'm just going to sketch the proof. You might also want to have Milne's arithmetic duality theorems chapter 1 nearby. Okay, here's the proof. So let S be a finite set of places of Q that contains infinity on the one hand, all the places with residue characteristic dividing the cardinality of M on the other, all the places at which M is ramified on the other, and all the places for which LV isn't just the set of unramified classes, H1 GV mod IV M to the IV on the final hand. Denote by Q sub S the maximal extension of Q that's unramified outside S, and let G sub S be the Galois group of Q sub S. If you just unravel definitions, you discover there's an exact sequence from 0 to H1 curly LQM to H1 GSM to the direct sum over all places V and S of H1 GVM mod LV. And from Milne chapter 1, we know that this guy is finite. I think CSS also takes care of this. And so since this guy, who injects into him, must also be finite. So H1 curly LQM is finite, and that is one of the things we wanted to prove in proposition 1. Okay, how do we prove that fancy formula with all the quotients and the big product? That is as follows. If we dualize this sequence for M star and apply local Tate duality, we get another exact sequence out of this. Okay, so what is the dual of this guy? The dual of that guy is just the direct sum over V and S LV. The dual of this guy for M star is H1 GSM star V or wedge. The dual of this guy is H1 curly L star Q M star dual or wedge or V or whatever you like, and then to 0. Okay, so we kind of turn like a left exactness into a right exactness. Okay, and then by Poitou Tate, and you can see Milne chapter 1 for this theorem as well, and I think CSS also deals with this. If C denotes complex conjugation, then we have the following exact sequence. So this is a big exact sequence, so get ready for this. 0 to H0 GSM to the direct sum over V and S of H0 GVM mod 1 plus C times M to H2 GSM star V to H1 GSM to the direct sum over V and S H1 GVM to H1 GSM star V. What's going on with this quotienting out by 1 plus CM? All that's happening there is we're thinking of 1 plus CM as living in H0 G infinity. And remember, S contains the infinite place. Okay, so we've got a massive exact sequence here. Let's go on. In this sequence, if you replace H1 GVM by LV for V and S, because that's what it is, and you combine the most recent two exact sequences, the one we just got done writing down, the big one, and then that dualized sequence right before it, there's no tricks to this. You just get the following new exact sequence. 0 to H0 GSM to direct sum over V and S, H0 GVM mod 1 plus CM to H2 GSM star V to H1, this is where it starts to change, to H1 curly LQM to direct sum over V and S of LV to H1 GSM star V to H1 curly L star QM star V to 0. Okay, so this is just kind of a write it down thing. And this gives you almost the entire result that we're after if you just compare cardinalities of all these guys now using like how cardinalities work within exact sequences. You get the following. You get that the cardinality of H1 curly LQM over the cardinality of H1 curly L star QM star is the cardinality of H0 GSM, cardinality of H2 GSM star V, times the cardinality of 1 plus CM, divided by the cardinality of H1 GSM star, times the product over V and S of the cardinalities of the L sub V's divided by the cardinalities of the H0 GVMs. And you're pretty much done now. You just need basically to deal with this guy and make him look like you want him to look, and then make sure certain sizes of certain modules match up. And they all do. I'll just tell you like the key thing to finish now is the global Euler characteristic formula, which you can see in Milne chapter 1, for example. Again, I think CSS and DDT also fill in the missing details here. Basically, if you kind of reciprocate this guy, so if you look at the cardinality of H1 GSM star divided by the cardinality of H0 GSM star, which will be the same as this guy. And then the cardinality of H2 GSM star, which literally, well, it's the same as the cardinality of this guy. You can prove that as well, although I think that's pretty eminently believable if you're just willing to buy it. And then you also kind of divide by the cardinality of 1 plus Cm. You could view this guy as just living in the denominator down here. That turns out to equal the cardinality of M star divided by the cardinality of H0 G infinity M star. And if you kind of plug that in and you make sure the sizes of everything match the formula from proposition 1, you actually get proposition 1 kind of immediately. Okay? So again, I didn't work out quite all the details here, especially in this last part. It's all there, modulo some kind of smaller things though. So we will continue on towards looking at the next crucial proposition for R equals T in the minimal case next week. I will see you then, and thanks for watching.